I was the science in charge of observation.
Johnny's mine. You'll just take this.
I'll send them to you as well. Mine are okay. All right, can you hear me? Yeah. Okay, let's go ahead and get started. Welcome everyone to the High Energy Seminar this week. We have two NPP postdoc that just won, so congratulations. We didn't mean for that to happen, but I think I just have a software. All right, so I'm happy to introduce first up today, we have Gabriel Grell. He's in his final year PhD candidate at the University of Maryland, College Park, and research assistant at the NASA Goddard Space Flight Center. And he works under the guidance of Dr. Maurice Lettniger at and the X-ray Astrophysics Laboratory. His major works have involved atomic physics calculations to construct and analyze theoretical spectral models for comparison with laboratory measurements and spectral observations from Chandra and XVII Newton. He did his undergraduate here, actually, in astrophysics and physics at Harvard, and then he continued research under Dr. Randall Smith, and he graduated in 2018. He's planning to continue at NASA Goddard as a postdoctoral fellow, and he's defending his dissertation this summer. So with that, take it away.
Thanks, Amy. Hi, everyone. My name is Gabriel, and again, I'm a PhD candidate at University of Maryland, College Park, and this is my talk on laboratory benchmark of neon-like iron-17 line formation channels using a device known as an electron beam ion trap, or EBIT for short. So just to give a brief intro about myself, my chief research focus is in the fields of theoretical and laboratory X-ray analysis. So since 2019, I've been working under Dr. Maurice Lettniger and the Goddard X-ray Astrophysics Lab, and my primary research focus has been in modeling X-ray spectra from hot plasmas in the megakelvin temperature range, specifically looking at the highly charged ion spectra that exist in these plasmas. So of course, X-ray photons are photoabsorbed by Earth's atmosphere, so we're heavily reliant on space-based spectroscopy and subsequent spectral modeling to fully interpret the X-ray universe, as I've constructed in this pipeline here. So just to give a brief overview of my presentation, I'll delve into some background information before explaining both the experimental and theoretical aspects of my present work. I'll then discuss my benchmark results and conclude with future directions and conclusions. So, as I alluded to in my intro slide, my primary focus is in highly charged ions, which is the predominant form in which most elements appear as in the visible universe. We see these ions in and around.
We're doing like this weird, like flashing.
Oh,
that same thing, yeah.
That's true. Let me just exit out all the other tabs. Here.
Sorry to mess with your phone.
No, it's okay.
I think that
Is that better?
That might be the PDF, actually.
Yeah, okay, I'll just minimize it for now.
Yeah, let's see if that does it. Okay, I think that looks good.
Okay, cool. All right. Okay, yeah. So yeah, HCIs are the predominant form in which most elements appear as in the visible universe. We see these ions in and around stars, stellar plasmas, X-ray binaries, elliptical galaxies, galaxy clusters, the list goes on. And the spectral emission lines from these objects are rich with HCI spectra, particularly in the X-ray regime. And they are very useful because the line ratios that can be derived, we can then use as diagnostics for key astrophysical parameters. These include using line shifts to study stellar dynamics, such as inflows and outflows. We can study temperature and ionization diagnostics using line strengths, line widths to study velocity turbulence. So the possibilities are really very bountiful when it comes to these kinds of studies. And the ion that's been my primary research focus has been a neon-like iron, otherwise known as iron 16 plus or iron 17, which is one of the strongest signatures of any highly charged ion in the X-ray regime. So neutral iron has 26 electrons. So in this case, 16 of them are stripped off and 10 remain. Therefore, it resembles a neon-like system. And this ion has one of the most stable and abundant charge states because it's a closed shell configuration and it has a very high ionization potential. And I particularly look at its L shell transitions, so transitions of electrons in and out of the n equals 2 subshell. So the astrophysically important transitions in this case are the 3C, 3D, and 3E transitions that demarcate the 3D manifold, and the 3F, 3G, and M2 lines that make up the 3S manifold. And because these lines are so prevalent in so many astrophysical objects in the X-ray regime, they represent very potentially very useful diagnostics for hot plasma conditions. And these include electron temperature, electron density, and optical depth. And so what are the mechanisms that are making these lines so prevalent? So the three dominant line formation channels are direct electron impact excitation, which involves a free electron colliding with a bound electron in the system, which causes the bound electron to excite from 2p to 3d, and also a process known as dielectronic capture, in which a free electron is captured while a bound electron is simultaneously excited, which creates an intermediate doubly excited state. And this intermediate state then has two possible final states. Either A, one of the electrons spontaneously autoionizes, which results in resonant excitation, or radiative decay occurs where one of the electrons is recombined, thus resulting in dielectronic recombination. So all three of these processes are primarily responsible for the strong presence of iron 17 in hot plasmas. However, even though it's potentially useful, there exists a very large roadblock for truly unlocking iron 17 as a useful diagnostic. And that is that there are significant disparities between the observational, theoretical, and experimental calculations of the iron 17 line formation channels. So several studies over many decades have found that there are model to data disparities on the level of 10 to as high as 30% for the 3 to 2p DE cross sections. So I'll direct your attention to this plot here from SHA 2019. So the blue, green, and orange curves that you see here are all different theoretical predictions for these cross sections for 3D to 2P. And they all exhibit 10 to 20% overestimations of the experimental cross sections, which is shown in the black curve here. So this is a huge issue because it really significantly hampers the diagnostic utility of these lines. So these issues highlight the need to measure the other key line formation processes, such as dielectronic recombination and resonant excitation, with better constraints. And these better constraints not only to probe what is causing the discrepancy, but also for potentially major astrophysical implications. So one example would be, there has been a well-known and useful diagnostic that measures the DR satellite lines and takes the ratio over its parent resonance line to obtain a very robust electron temperature estimation. So a study by Beiersdorfer 2018 tried to use this for the iron 17 regime, but found that in order to match the astrophysical plasma derivation from the stars Capella and Procyon, they had to reduce the theoretical prediction of the iron 17 3C line intensity by 30%, which goes to show that there is a huge gap between where our theoretical models are and what we're actually seeing from experiments and from astrophysical observations. And it's already manifested in studies attempting to use iron 17 already, as disparities lead to very significant systematic uncertainties in spectral studies, which severely limit our interpretations and the conclusions that we're able to draw. So for example, Deplat 2012 attempted to use the 3G plus M2 over 3C line ratio to derive turbulent velocity estimations in elliptical galaxies. But due to the systematic uncertainties, they found that just a 15% ratio increase led to a factor of 2 difference in the velocity calculation. So I'll direct your attention to this plot over here on the left. So the curves you see, the dotted one and the solid one, are both 2 different theoretical predictions from widely used atomic databases, AtomDB and SPECS. The plot point you see with the cross is a tokamak measurement, which is a device you can use for experimental measurements. So all 3 of those are giving 2 very different estimations for the ratio. And so when trying to draw an astrophysical conclusion from the galaxy plot points, so NGC 5813 and NGC 5044, it's very difficult to draw any kind of conclusion for that because the true value is unknown. So it goes to show that the current models right now are not yet sufficient to answer questions like these. And so the next step would be to have more comprehensive laboratory measurements in order to benchmark theory with better constraints.
I think we didn't turn it.
Oh. More technical difficulties.
I can hear you.
Is there like a button to press?
Yeah, she can.
Yeah.
Okay. Hello?
Yes.
Okay, cool. Okay, so now beginning the meat of my presentation. So my objectives for this work were to calculate theoretical cross sections for the DR, RE, and DE line formation channels of iron 17 and benchmarking those predictions with experimental measurements from an electron beam ion trap. Then extend the benchmark for previous investigations to all of the observable channels in the experimental data set. And finally, infer rate coefficients, which are resonance strengths integrated over a Maxwellian velocity distribution in order to compare our findings with values available in atomic databases. So I'll start off with our experimental measurements. So theoretical calculations of line formation processes can be effectively benchmarked by experiments using electron beam ion traps, or EBITs for short. So EBITs use an electron beam focused with a strong magnetic field in order to ionize atoms to high charge states by successive electron impact. So I liken EBITs to a kind of particle accelerator in which we are taking advantage of magnetic and electric fields in order to produce particles that otherwise would only exist in the plasmas of stars. So as one of my advisors put it, we are harnessing the power of the stars to learn more about them. So EBITs have proven to be a key instrument in X-ray lab astrophysics, both for benchmarking theoretical models and also for calibrating future space-borne spectrometers, such as the Prism Resolve instrument. So EBITs conduct highly charged ion experiments by sweeping the electron beam energy over the photon energies of the ion resonances that we wish to study. And the ion produced can reach up to 10 to the 7 Kelvin and therefore rival some of the hottest plasmas in the universe. So how do EBITs work? So an EBIT operates by means of a quasi-monoenergetic electron beam, and which induces a negative space charge potential. So starting from step 1, the electron beam is emitted from an electron gun and guided along an axis of cylindrical drip tubes until reaching a collector electrode. Step 2, a strong magnetic field compresses the beam to a sub-millimeter diameter at the trap center, which results in a very high current density for ion trapping. Then with these, the electric and magnetic field setup, neutral atoms are then injected into the trap by introducing a gas or a compound through an injection pump system. And then finally, the atoms are ionized by successive electron impacts and trapped by the potential applied to the drip tubes. And it is these collisions between the beam electrons and the trapped ions that effectively drive the line formation processes that we wish to study, so the recombination, ionization, and excitation processes. It's kind of loud. Yeah. So with that in mind, I'll now highlight our specific experiment, which we used from the flash EBIT in Heidelberg, Germany. So we use flash EBIT to produce a population of iron 17 ions by shooting an electron beam at a compound of iron pentacarbonyl. Iron pentacarbonyl is an organometallic compound, so it's kind of this oily yellow liquid, and we vaporize that to then inject it into the EBIT system. So the electron beam energy was swept over the energy range of the iron 17 dielectronic capture resonances. So, and I highlight the beam energy scan technique that we use. So starting from 1.2 keV, where we're able to ionize iron 17 atoms, we then followed that up with a short ramp down 300 eV and a symmetric ramp up back up to 1.2. By doing this, we effectively maximize the iron 17 ion purity by sufficiently suppressing the lower charge states from recombining. So the radiative decay of the excited states then generated X-ray photons, which we then collected using a silicon drift detector. The photon energy resolution of this STD was about 120 eV and 1 eV. So that's our experimental side. Now on to the theoretical aspect. So in order to use our data to infer properties, we must construct spectrum models to try to match the data as closely as possible. The better the fit, the more we can infer from the comparison. So in order to model the atomic structure of a particular charge state, in this case iron 17, we made use of the flexible atomic code software package, which allows you to take into consideration a multitude of different physical processes that are listed here, like radiative transitions, photoionization, photoexcitation, and specifically for our case, RE, DE, and DR. So, and in fact, integrates all of these processes into a singular framework and allows you to then calculate accurate level populations. And this is key to include all these different processes because we must consider all the processes that could populate and depopulate a certain level. So for our specific model, we calculated line emission cross sections for the DR, RE, and DE channels by considering all the configurations that I've listed here for inner shell level and up to n equals up to 7, valence shell level up to n prime equals to 100, and angular momentum quantum numbers L up to 8 respectively. Without getting into too much of the atomic physics, this was basically to ensure that there was a convergence in our configuration mixing, which is basically a brute force way to make sure that all the levels that could possibly appear in the experimental data set, we would also have in our theoretical predictions. So we use fact to calculate the cross sections here, and we account for the satellites producing both the 3D and 3S manifolds, as well as the higher energy DR satellites, which we are focusing on for this present work, in order to complement previous investigations that focused on the n=3 satellites. In order to run this calculation, we made use of the NASA Discover supercluster to run the calculations, because on a local computer, it would probably take a week, but in a cluster, just a few hours. Okay, so now on for our benchmarking results. So I'll first highlight some of the previous works that use this experimental data set. So Shaw 2019 used flash EBIT in order to determine the relative 3S and 3D line emission cross sections, and in doing so published the first laboratory measurements of the intensities and cross sections for the DR L-shell satellites for the LMN series. So these peaks that you see here are all different DR LMN resonances. So this is a comparison of the experimental DR cross sections, and in order to have a direct comparison of the cross sections, they normalized theory to experiment by using a singular DR peak whose strength can be traced to a single and strong resonance, and therefore make a better and more theoretically reliable prediction. Then Grell 2021 followed up the study by providing new experimental resonance strengths and rate coefficients for the DR LMM satellites. So rate coefficients, again, are resonance strengths integrated over a Maxwellian velocity distribution and are very useful parameters for studies of charge balance and plasma diagnostics. So in doing so, they compared the rate they calculated to those available on atomic databases, including OpenAS and AtomDB, and found considerable discrepancies on the level of 2 to 3 sigma. So now on to our present work. So the top plot you see here is the measured X-ray intensity produced from the flash EBIT experiment, independence of both electron beam energy and X-ray photon energy. So what you're seeing is really a 2D histogram contour plot using the energies as bins and the intensities as the contour values. And the distinct plot features that you see are all of the DR, DE, and RE contributions at the iron 17 transition lines. And by taking a region of interest cut along the X-ray energy, as you see from the red box, we're able to then make a plot of the photon counts from our experimental data set. And then we normalize our theoretical predictions using the same methodology from Shaw 2019 by using a single peak that has only a single resonance included within it, to then make a direct comparison of the cross-section values. So the bottom plot you see here is comparison of the n=4 DR and DE satellites. And we see both 20 to 25% overestimation of both contributions. And I'll direct your attention to these features here that appear to be missing in the theoretical predictions, when in actuality, they're actually resonances from the higher energy satellites that are bleeding into our ROI. So why is that happening? So due to flash EBIT's silicon drift detector's resolution, which is again about 120 EV, when making an ROI cut on the experimental data set, the spectral histogram that results loses flux from the resonances of interest and gains flux from the ones that we're trying to exclude. So to overcome this phenomenon, we employed what we call a forward folding approach by broadening the theoretical cross-section Gaussian functions in order to match the STD's finite resolution and the electron beam energy spread of the EBIT. So in doing so, we are folding the theoretical cross-sections through the experiment response. And in doing so, we're able to reproduce the blended features and give better fidelity for a direct model to data comparison. So we set the beam energy resolution to match flash EBITs of 5 EV full width half max, and the photon energy resolution we set to 120 EV to match that of the silicon drift detector. So now we have a direct contour plot comparison now that we have broadened our theoretical predictions with Gaussian functions, and now have all the distinct plot features from their experiment are now also visible in our folded theory dataset. And now by taking the same ROI selection method that we use, we now have a better agreement with the forward folded cross sections between theory and experiment. So by incorporating the forward folding approach, we were able to find better agreement within 10% and also a lower systematic uncertainty. And again, the missing features that were previously not shown in the absolute cross sections are now visible in the forward folded. And then the final step was then inferring rate coefficients from these cross sections, not the forward folded. So we're answering two different questions here. So in this case, we're benchmarking FAC and comparing it to available atomic databases. And the previous step was to explain our experimental measurements as closely as possible. So in this case, we found reasonable agreement with both our experimental data and OpenADAS results within 2 sigma. The total integrated cross sections are also within 2 sigma, but the disparities become a bit more significant at the lower n complexes, particularly the LNN series at the bottom. However, because these are significantly smaller, they are less consequential than the higher energy ones. So conclude with future directions. So one potential experiment to improve our results would be to repeat the flash EBIT measurements with a wideband high resolution microcalorimeter. This device is a thermal detector that measures the heat of an incoming electron that is incident upon the detector and would provide a much improved photon energy resolution than compared with a silicon drip detector. So this result in a much better ability to resolve the individual transition lines and therefore significantly reduce the systematic uncertainty of the experimental data. So continually improving these experiments in order to provide smaller uncertainties is necessary in order to fully enable and unlock the spectral diagnostics of iron 17 transition lines. So, and just to give a potential showcase of what that would look like. So the top is again the flash EBIT contour plot, and by significantly improving the photon energy resolution, we'd be able to more easily resolve the individual DR, DE, and RE features. And then when selecting the ROIs, we would be able to capture most of the counts associated with each transition, and therefore reduce the uncertainty from the normalization. So just to conclude, we compared our cross-section calculations for the line formation channels of iron 17 and benchmarked our predictions with those extracted from the flash EBIT experiment and extended the experimental benchmark from previous studies to the higher N resonances. We improved on previous work by applying our forward folding approach to find agreement within 10%. Our work will hopefully soon be published in the Astrophysical Journal. We just submitted a few weeks ago, and potential improvement of our experiment would be to use a microcalorimeter instead of an STD to allow significant reduction of systematic uncertainties. And with that, I'll take any questions.
Questions?
You know, you were using FAC throughout, but were you doing distorted wave calculations, or do you think it's more, okay?
Distorted wave, yeah.
And on the DR side of the coin, with this data, you would also be able to convert the observations into, say, a wavelength and a Q value for the DR and the excitation energy for the DR. Did you ever consider, instead of making it into a rate coefficient and changing that, taking the data and converting it back into the DR satellite line constituents themselves? Did you ever consider trying that?
No, that's a great idea though. So you're saying to convert it back into the wavelength?
Correct.
Okay. No, I should talk to Maurice and Chetan about that because that's a good idea. Yeah.
Many questions.
Okay.
So you picked one line for your normalization. Did you try like multiple, or, you know?
So I looked at just following Chetan's methodology, you know, I kind of looked out for the N=4 manifold, and that only one of the peaks had a single resonance included within it. The others had multiple lines, like all blended into the same peak. So in order to give the most reliable fidelity, we just stayed with the peak that would have one single resonance.
Okay. That was the only one you had.
Yeah.
I'll go get it. Nobody else is jumping with on physics, there's great on physics. At the highest N energies, your fit was going the worst.
Yeah.
Do you think that's because weren't converging, or do you think there was a data problem, or do you have any ideas as to why that things were going slightly, haywire at the higher energies?
That's a good question. In terms of the mixing the configuration that we did, we kind of did, went up to N prime and up to 100 in order to kind of rule that out as a potential explanation for any kind of discrepancy. So it's hard to say. So the higher ends are much lower in resonance strength, so therefore, we can kind of rule them out for any kind of applications for astrophysical studies, since they're, less consequential. But yeah, that is something to still that's still yet to be explained why it's not converging yet.
Some of the photons emitted in EBITs are polarized and anisotropically emitted. Is that true for these?
Yep. So we made use of FAC's polarization module in order to take account of the polarization and anisotropic emission.
One last question. How much longer will the microcalorimeter measurements take you?
Well, first it has to be the microcalorimeter has to be built. So TBD.
Okay, all right, well, thank you. Okay, one more time.
It's just. Here and then. Let's go.
Yeah, that's very strange. You disconnect and reconnect.
Yeah, for some reason the video goes.
Let's just like stop the video and start it.
You just needed a.
That's very weird. Meeting now. Is that owl like asleep?
So you have to get a.
Does it fall asleep?
The lights are.
Okay, let me switch to his.
Yeah, we might just have
Camera?
to use your.
It's not working.
Maybe stop sharing.
Okay, let's. Okay, and then should we do it again?
Yeah.
Let's try meeting owl again.
We might just have to do that video.
Okay, that is very strange. Can we, okay, that part worked. I'm not sure what's going on.
And it must work, but what if we disconnect the meeting now, then does his computer camera work?
I tried that and it didn't work
Like
either.
a physical disconnect?
Physical disc.
No.
It's still not working. Wow, this has been like the most technical difficulties we've ever had, I think.
There's nothing, right?
No, there's no.
Okay, well, we'll just be videoless if that's okay with you.
We'll just post a picture of you.
Sure.
Sorry,
Okay,
Are we still going through this microphone then, or will we have to change that?
the mic should be fine. Can you hear it?
Yeah.
Okay. Sorry about that. You can't hear me.
Yeah, that's not.
Is it okay?
Yeah.
Okay. So Tyler Holland-Ashford got his PhD from the Ohio State University in 2021 and has since held the future faculty leader position, postdoctoral fellowship at the CfA. His work involves analyzing X-ray observations of supernova remnants and any compact objects embedded within. So studying supernova remnant morphologies, neutron star kick velocities, and plasma properties of the X-ray emitting shock heated ejecta. This fall, he will also begin an NPP position at NASA's Goddard Space Flight Center, which we just happened to get both of them to give a talk here today at the same time, working on PRISM, a recently launched X-ray microcalorimeter telescope, observations of supernova remnants. So the title of his talk is Measuring Ejecta Mass Ratios in Kepler's Supernova Remnants to Constrain Its Origin. And go ahead.
Great, yeah, thanks for that introduction. You said the title and my name, so I'll just get on with it. In general, my work as an astronomer so far has been geared to understanding supernovae, the explosions of stars at the end of their lifetimes. In general, there's the two big categories: core collapse, the explosions of massive stars once they burn through their fuel in their interior and collapse and then rebound back, or type 1a thermonuclear explosions of white dwarfs after lower mass stars eventually turn into these white dwarfs and then interact with a companion to explode. And the supernovae are extremely important for understanding essentially everything in galactic evolution, as they are these incredibly energetic, incredibly bright events that can outshine entire galaxies. Here, for example, is a image of a supernovae compared to an entire galaxy. And as they do this, they impart energy into their surroundings, affecting galactic winds and feedback that can regulate future star formation. And they also synthesize a lot of the heavy elements that are then spread out throughout the entire galaxies, and then in turn form new generations of stars and planets with these metals. And there still remains a lot to be understood about supernovae. Their relative rarity, with about a few per galaxy per century, means that a lot of the ones that we see, are very, very distant. And it's much harder to gain any information about things that are distant. You get less flux, you can't spatially resolve them. And there's a host of different properties that will affect supernovae: the progenitor mass, the rotation, any magnetic fields, a whole host of different types going into different types of explosions, which we all need to understand. And so for my talk, I'm going to focus us down on type 1a thermonuclear explosions of white dwarfs. And broadly, there can be two categories of these. You have you can categorize them by their companion type, either a double degenerate on the left here with another white dwarf as its companion, or a single degenerate with a non-white dwarf companion, typically a post-main sequence star. And in the double degenerate case, the classical explanations, you have two white dwarfs that inspiral due to gravitational wave emissions. Eventually they combine and explode. And single degenerate, the classical is you have accretion from this post-main sequence star exceeding its Roche lobe, accreting onto the white dwarf until it exceeds the Chandrasekhar mass of about 1.4 solar masses and then explodes. But there are more ways to categorize type 1As. It's not exactly as simple as this. There's also the mass of the progenitor, which is somewhat related to the degeneracy. Near and sub Chandrasekhar mass explosions. Near, again, is that 1.4 Chandrasekhar mass limit, and sub is if white dwarf explodes at below that limit due to whatever intrinsicies of the accretion or the collision between the white dwarfs can cause it to explode earlier. And these things have different predictions for example, nucleosynthesis of heavy elements. And we can look at sample star populations and star metallicities to help us constrain this and try to figure out, which formation mechanism dominates near or sub Chandrasekhar mass. And so here is a plot showing observed manganese to iron and iron on H abundances in stars. That's all these data points. And the red curve is what if you had all type 1a explosions were near Chandrasekhar mass. The blue is what if you had all were sub Chandrasekhar mass. And as is clear, neither of those match the data. You need some combination of both near and sub Chandrasekhar mass explosions. As in most things in astronomy, is when you have two competing scenarios and you ask which one is it, it's probably both. And so these are some of the most common ways to distinguish type 1As or to classify them. But then I also want to emphasize another way. So instead of looking at the companion type or the mass of a white dwarf when it explodes, you also look at the accretion style during that leads to and is immediately prior to explosion. So here is a chart showing on the left column, it's the type of companion. The top two rows are these post-make sequence stars. The bottom three are the companion white dwarf. And then the right two columns are showing different core masses, Chandrasekhar versus sub-Chandrasekhar mass, and different types of detonations. And so everything that's plotted on here is kind of what I've talked about before, the single degenerate accretion or the double degenerate merging. But then there's also these other types, these so-called double detonations, where instead of having accretion until you reach this Chandrasekhar mass, you accrete and a helium layer starts to form on the outside of the white dwarf. And then eventually, once that helium layer reaches a critical mass, it will explode in a detonation, which will then induce a second detonation in the white dwarf, causing it to explode, possibly much prior to that Chandrasekhar mass limit. And then there's an even more complicated version of this, the so-called dynamically driven degenerate double detonation, where instead of having slow accretion onto that forms a large helium layer which detonates, you have some type of unstable accretion, which then will ignite before or earlier on when there's only a thin helium layer due to the sloshing motions that's it's dynamically unstable accreting, which can lead to an explosion earlier on. Which one phenomenon of this is that you can explode early enough in these two white dwarfs' lifetime where that the white dwarfs are still sufficiently far away. So when the primary explodes, the secondary can actually remain. And you might actually be able to see this looking at the remnants of an explosion. This would be a smoking gun of this type of detonation. And so all of these are different possibilities, different types of 1As that can happen. And of course, trying to figure out what are the percentages of each that, and how are they formed, what types of masses and rotations, etc., lead to these explosions, and what do these explosions produce in terms of energetics and nuclear synthesized material are things that I am interested in. And so I look at supernova remnants, as I mentioned. Studying supernovae directly can be hard because they're so distant, but supernova remnants have exploded in our galaxy tens of thousands of years ago, or maybe just even a few hundred years ago, and they will expand through our galaxy and get bright as they generate forward shocks and then reverse shocks, which come back, sweep in and heat all of the ejected material to millions of degrees. And because they are expanding and so bright and in our own galaxy, we can observe them in high resolution, like for example, this Tycho supernova remnant pictured, where you can see individual clumps in this remnant, and then also by looking at the X-ray energies, that photons that come in, you can associate different types of emission with different elements, emission lines from like silicon and sulfur and argon, iron, and then use those informations to constrain the amount of materials that were produced, the plasma properties of the remnant and its energetics. Here's just what I've talked about. You can get information about, you can look for a surviving companion, you can look at its shape, and you look at the metals and plasma properties to learn more about remnants, and then use that information to learn more about their progenitor supernovae. And so I'll tell you about my work, recent work I've done on analyzing the X-ray spectrum to estimate the total mass ratios in Kepler's supernova remnant. Here is Kepler's supernova remnant shown on the right. And on the left is its X-ray spectrum going from 0.6 to 8 keV. And you can see that this is the overall broad spectrum, broadly thermal Bremsstrahlung emission of millions of degrees plasma. And then you can see strong emission lines from these different elements that I mentioned, your silicon, sulfur, argon, calcium, iron, and then even smaller ones down here in the bottom from iron group elements, chromium, manganese, and nickel. And in particular, these iron group elements down at the bottom are various types of 1A simulations produce differing amounts of these elements. And so these manganese in particular, looking at the ratio of manganese produced to iron, is a strong predictor of the type of explosion. And so my goal was to measure the total mass ratios of elements synthesized in Kepler's supernova remnant and then compare them to the predictions of models. And so as I was doing the entire remnant, because I wanted to get the full ejecta mass ratios, not just some in one part of the remnant, but as you might realize from looking at these objects, they are incredibly complex with different plasma properties, different ejecta abundances, et cetera, in different places of the remnant. And so it requires a fairly complicated model. And through testing and seeing what model would that fit best with the data and accurately capture all the emission, I ended up with a 5-component model, one from swept up interstellar material that is heated and is not really relevant to the nucleosynthesized ejecta, but still needs to be accounted for to essentially subtract out any contribution from swept up material. 3 ejecta components at different temperatures and with different abundances, just to reflect different parts of the remnant which have more iron than more silicon, and also to capture parts that have been had different ionization histories, potentially are further out in the remnant versus closer to the core and have different temperatures too. And then also one final synchrotron emission to capture non-thermal emission, mainly at the shock boundary at the front. And so fitting these models enables me to fit these models can constrain plasma temperatures and plasma, importantly, ejecta abundances, which then I can turn into masses to compare to the predictions of simulations. And then one thing I do want to focus on is that this fit, it looks pretty amazing here. I mean, if I didn't tell you there was a line going through all the data points, you might not be able to see it. But this model fits the data fairly well, except when you go to look at the residuals. And you can see that the bottom left, particularly, that residuals go up to 5. And so across the entire energy band, this fit has a reduced chi-squared of 3, which isn't great statistics-wise. And so one of the parts of this project was to investigate, okay, what's the problem here? As Gabe talked about, is this a problem with atomic data? Do we not have precise enough atomic data to be able to map what we actually observe in remnants? Is this a problem where my model is too simple to capture the incredible complexities and differences in different spatial parts of the remnant? And I investigated those a little bit, but then found out that one of the main problems was that the data, I simply had too much data to be able to really do this analysis, which is not a problem you usually have in X-ray astronomy. But supernova remnants are just so big and bright that we can get millions and millions of photons, which turns the Poisson uncertainty in the photon counts to essentially 0. So it treats every data point, every count per second per keV as essentially almost, I mean, not quite infinite precision, but very, very high precision. So any small discrepancies between the model and your observations and between the data will have large reduced chi-squared. And so what I found was that telescope uncertainties that are often not included in X-ray analysis are of the order of 5 to 10% level. They actually do need to be included when you have this high signal data, because these 5 to 10% actually matter, actually dominate over the less than 1% photon Poisson uncertainties. And so I was able to do so, incorporate those errors in the Suzaku telescope using estimated effective area uncertainties. So here is the effective area curve of Suzaku plotted in black, just the response, the collecting area as a function of energy. And by using the estimates of the accuracy of these effective area calibration, I was able to generate 100 mock effective area curves in all these different colors, which essentially represent the spread of possible true calibrations of the Suzaku telescope. And so then by fitting the data to 100 of these effective area curves, I was able to get 100 sets of best fit parameters. So here is just showing a sample set of the temperature for one plasma and the temperature for another plasma, the best fit values. And if you focus in on, let's say this central blue clump here, this is for one single run of those 100s. That is the best fit plasma temperatures using one mock effective area curve. And the size of this and the location essentially would be the average mean value plus or minus the standard deviation. But then when you when you account for all the different other possible effective area curves, you see that the spread is much larger than any one of these individual globs, which just emphasizes the importance of accounting for these uncertainties, or else if you just use one blob, your best fit value will be much too precise than it actually should be. And so in doing so, I was able to accurately measure and record the uncertainties in these mass ratios, which is important then for comparing that to simulations with robustness. And so finally, by doing that, I'm able to get these measured mass ratios by fitting the data 100 times, getting best fit abundances and turning those into mass ratios. Here is a plot just showing the the depth and the breadth of the mass ratios I was able to get for things from silicon to sulfur, argon to manganese, different mass ratios, which compared to other investigations of Kepler's supernova that have been done, others that focus on a specific part of Kepler or a specific energy range, but didn't do this full broad analysis of the entirety of the remnant over the largest energy bandpass with one self-similar model that can fit the entire spectrum. And so I was able to get more values than previous papers, and also it might be hard to see, but the uncertainties of my values, even though I was using this more complex error uncertainty calculation to accurately estimate the effects of this effective area uncertainty, my uncertainties and my mass ratios are actually more precise than a lot of these other investigations. And I think, again, this is because I used the entire energy band and we're using a self-similar model that enabled me to essentially use all the data I possibly could to constrain it, using both the high and the low energy to constrain this model as good as possible. And so then finally, I can plot these values against the values for simulations. So here are the mass ratios I found. It's just a sample selection of them. On the y-axis is calcium to sulfur. On the x-axis is chromium to iron. And the green contours are my 90% confidence intervals for the mass ratios I found. And then all the data points are from different simulations, the nucleosynthesis predictions of 1D on the left, 3D on the middle for delay detonation models, and then on the right is various predictions for double detonation models. Remember all those different possible types of type 1A supernovae explosions. And one striking detail I immediately found was that almost all of the models were under predicting the calcium to sulfur that I found. All of these data points are under my green contour or under the 90% contour. And this is, of course, very important because if they can't, if none of the models can reproduce the observed calcium to sulfur mass ratio, then you can't use any of these models to constrain Kepler's remnant, and the models might not even be correct. And so a solution I found for that was that some models use a 90% attenuation in a carbon to oxygen reaction rate, which is important for the somewhat middle to outer layers of the explosion itself. And when they decrease the rate by 90%, so only 10% as strong, a vast decrease in this reaction rate, they got calcium to sulfur mass ratios, which were much more in line with what I found. As you can see, all these data points are now within this wide bar green band. And so it seems like this is important for not only Kepler supernova remnant, but also they did this type of analysis on other remnants. And it seems like this 90% attenuation is critical for producing results that match with remnants, and so it needs to be done going forward using in other simulations if we want to get real results. And so that was for it. In addition, I can then say more about Kepler's supernova remnant, looking at the different models, taking into account only the models which essentially have this 90% attenuation rate in that carbon to oxygen. And so for looking at single detonations, I was able to find that the Kepler supernova remnant was consistent with both near Chandrasekhar mass or sub-Chandrasekhar mass models. Here on the right is just a plot showing example mass ratios for these models, and you can see that they intersect pretty well with my results. And so either sub or near Chandrasekhar mass are consistent, but both types are also require a relatively high metallicity progenitor, about 1 to 2 solar metallicities, and also a pretty energetic explosion that produces a lot of nickel, or in the sub-Chandrasekhar mass, still a fairly massive star at about 1.1 solar masses, so nothing that gets down to the 0.7 range. And so it seems like for at least these two cases that the progenitor would be have a high metallicity and be fairly energetic. And for double detonations, that other case where you have the helium layer accreting onto the outer of a white dwarf, for the stable method where you have that thick helium layer that explodes, I found that this was inconsistent to explain Kepler's supernova remnant. The chromium to iron mass ratios were just systematically too large. And for the unstable method, this D6 method, is possibly consistent if you extrapolate these data points to extremely high metallicities. So here goes from 0.5 metallicity to 1 to 2 solar. So if you extrapolate it up to 2.5 to 3, then maybe you could get consistent, and those should be tested in simulations, but that still would be a fairly infeasible metallicity for a star that was born so long ago, millions, billions of years ago. And so finally, I'll bring to my future work is to extend this type of analysis on a larger sample of remnants. This will especially help test if all remnants require this 90% attenuation in the carbon to oxygen reaction rate, or it's just a few slamful of them. And then also just being able to build a large sample to test more properties of simulations and get more constraints on the percentages and feasibility of different progenitor types. I hope to use the microcalorimeter prism data, which will have much improved spectral resolution. This black curve, this black spectrum instead of the red spectrum that is in current CCDs, enable us to essentially do all types of more precise work and constrain abundances, ion temperatures, and just in general improve our ability to extract information from supernova remnants. And so with that, I'll just leave you with the summary slide. This 90% attenuation in carbon and oxygen rate seems vital for matching observations of supernova remnants. And for Kepler's supernova remnant, single detonation over luminous models with high metallicity progenitors are favored. Thank you.
Okay, so now we have time for some questions. Anybody has questions?
The model itself seems pretty oversimplified with just 3 components. On the other hand, the uncertainties in the calibration seem like you may have already reached the point of diminishing returns. There would be no point in making the models fancier. You have any comment on that?
Yes, and so I did try using different models. I settled on this 5-component model because essentially using any number of fewer components clearly did not fit the data well, but then using more components didn't improve the fit statistically, and just made it take longer to fit. There is, I guess the key point here is that this model seems to still capture the data pretty well, especially when you do account for the systematics. And I don't think that including any more would really help given the 5 to 10% level of systematics.
Any other questions?
You're on the right slide. That's what I was gonna ask a question about. So, okay, so when you look at the residuals, you can see for a large part of that energy range, the residuals are correlated. The red, green, and blue follow each other. But the one region that really sticks out is the silicon-13 triplet, where the residuals are not correlated, the red, green, and the blue. And of course, we know there are 3 detectors here, and one's the backside and 2 are the front side. So you expect the backside and the front side, they don't agree with each other, they've had the gain problem. But here, all 3 of them are disagreeing with each other. So even the front side disagrees with each other here at silicon-13. So it looks like there's some sort of gain issue there that's affecting the front sides differently, and of course the backside. So did you try adjusting the gain to get a better fit around silicon-13 triplet, or?
I did not try adjusting a gain for the Suzaku telescope for the various different detectors. I believe that all of these are actually the same detector. They're all XIS0.
Oh, these are all XIS?
Yes,
Oh.
I use different observations that have been taken at different times, but all XIS0 to try to avoid that problem.
Oh, so that's an interesting problem. So there's a time dependence in the gains with silicon-13, because you see, other regions, residuals match each other.
Yep.
So you could either adjust your model, get a better fit, or say the calibration's wrong. But here, there's a time dependence. How many different observations were there?
I used 4 observations. Yeah, I mean, it seems like there is that. I mean, luckily the silicon, it has this largest peak, and so these slight residuals, are still pretty tiny in the scale compared to the scale of the peak, and so this wouldn't affect. Especially this wouldn't affect these manganese and iron mass ratios, which are really the strongest constraints on the simulations and on the nucleosynthesis. But yes, that is clearly, as you see, a difference between these detectors or between these observations.
Great talk, thanks. I just was wondering, do you have any sense of what might cause the 90% decrease?
Yes, so I mean, this is getting much more deep into the atomic physics side of things. From looking at papers, it seems to be a cross-section uncertainty when determining the reaction rate. There's, I think it's Coughlin and Fauci paper in 1988, something along the lines of it's in a region where there's interference between multiple resonance regions, and that's my understanding of it. But it seems like, yeah, some type of lab physics calibration uncertainty.
Okay, any other questions? All right, well, if we're done with questions, let's give both of our speakers another round of applause.